Cold Central Plant Recycling, or CCPR, is a way to reuse old in-place pavement materials to make new pavement. Instead of heating all the materials like in traditional asphalt recycling, CCPR mixes them at ambient temperature. Emulsified or foamed asphalt is used as the asphalt stabilizer, with small amounts of cement or lime that serve as an active filler. It uses less energy and fewer raw materials than traditional asphalt production. Cold recycling can be done either in place or using a mobile central plant. Mobile plants have a small footprint and can be set up on-site to minimize hauling. Compared to in-place recycling, plant operations offer greater versatility, improved material control, and the ability to place thicker layers. Research is underway at the Federal Aviation Administration's National Airport Pavement and Materials Research Center to find out if the technology is suitable for airfields.
A lot of what we do in research is very iterative based, and this is kind of jumping in with both feet and seeing if it works.
We haven't in the past known enough about how it will behave under an aircraft load. We've got there on highway pavements now, so the idea is, with our better understanding, can we start implementing it on airfield pavements? The beauty of this facility is we can try different things, not going to hurt anybody, and if we get it right, then we can start an implementation process from there.
On highways, vehicles typically carry loads of up to 5,000 pounds per wheel, with tire pressures around 100 pounds per square inch. On airfields, the demands are far greater. Commercial aircraft can exert loads of up to 72,000 pounds per wheel and 250 pounds per square inch tire pressure. Researchers are testing whether CCPR mix can withstand these extreme conditions.
Durability of the material is very important because any cracks that are not sealed could result in chunks of material that could cause fault issues for an object debris, and these loose pieces of material can be easily sucked up into the engine of an aircraft and can cause severe property and life damage.
6 pavement test lanes are being used to compare standard FAA P401 pavements with various CCPR designs. These designs focus on recycling to the bottom of the distress, increasing structural capacity, and using all available on-site materials. Some lanes recycle only the asphalt layer, while others incorporate both the asphalt and aggregate base into the recycled layer. Each lane uses different asphalt stabilizers. Sensors installed throughout the test sections collect data in real time, allowing engineers to monitor changes in stresses and strains over thousands of aircraft load cycles. The goal is to determine whether recycled materials can match or even exceed the performance of conventional base materials. To make a quality CCPR mix, you need 4 ingredients: reclaimed asphalt pavement or RAP, an asphalt stabilizer, water, and active fillers like cement or lime. CCPR starts with recycled pavement materials, including RAP and crushed stone base. These are old pavement materials that have been milled off the airfield or brought in from storage. In CCPR, emulsified or foamed asphalt are referred to as asphalt stabilizers and serve as the main binder in the mix. Emulsified asphalt coats the RAP using a water-based solution that can be engineered for specific conditions. Foamed asphalt uses heat, water, and air to expand the binder and distribute it through the mix. Recycling additives are mixed with the recycled materials to improve strength and moisture resistance, and corrective aggregates help adjust the particle size for a consistent mix. Before any CCPR mix is made, engineers design a job mix formula, or JMF. This recipe determines gradation, specific gravity, tensile strength, and the type and amount of asphalt stabilizer to use. Unlike traditional asphalt mixtures, CCPR does not require specific fine or coarse aggregate tests. However, the mix must still meet requirements for properties such as gradation and the asphalt binder to active filler ratio. Because CCPR reuses in-place materials, it doesn't require as much testing of virgin aggregates, but it's still important to control the ratio of binder to additives. Too much cement or lime can make the pavement brittle and crack. For emulsified asphalt, the JMF also tests how well the RAP gets coated and checks temperature limits. For foamed asphalt, it includes foam expansion, half-life, temperature, and foaming water content. RAP must be crushed and screened for a consistent size. Then it goes into a cold feed hopper and onto a conveyor belt with a scale. A cold mix plant uses components like a hopper, belt scale, additive systems, and a pug mill for mixing. It precisely controls the ratio of wrap, corrective aggregate, asphalt stabilizer, water, and fillers according to the mix design. To produce an emulsified asphalt mix, an asphalt stabilizer is pumped from the tank to a spray bar that distributes it directly into the mix. Foamed asphalt uses a spray bar with a small expansion chamber above the nozzle, where hot binder is mixed with air and water to produce foam. Most plants can produce both emulsion and foamed asphalt mixes. CCPR must be hauled to the paving site and placed and compacted within 2 hours. To maintain continuous paving, the entire operation must be carefully coordinated, matching plant production with placement on the grade and timing trucks to support both without delays. Placing CCPR is similar to traditional asphalt mixtures. Most jobs need heavy rollers, a 10-ton vibratory roller and a 20-ton pneumatic roller, sometimes heavier, depending on layer thickness. It's important not to heat the screed, since the mix may stick to the equipment. Quality checks include many of the same tests used for asphalt mixtures, including density, moisture, temperature, and gradation. Other quality control tests for CCPR include in-place shear resistance, asphalt stabilizer rate, indirect tensile strength, and the wrap to corrective aggregate ratio.
CCPR also has a curing factor. You can't hot mix, you can make it that day, test it, and have results by that evening. CCPRM could take up to 72 hours, if not 96 hours, to get results. So when you do trial sections, they typically are done weeks in advance. And then once you start producing a product and you have data points that you can look at, you can start being more comfortable with producing the product on a daily basis and not having your test results until 3 or 4 days later.
I think that's one of the important things of this project, is trying to understand the strengths, but what also are the limitations that we need to write careful specifications around to, if one day we're using it, ensure the best performance possible.
To accept a CCPR mix, it must meet standards for compaction, strength, smoothness, grade, and thickness. Additional tests check the asphalt stabilizer dosage, active filler content, and gradation.
The benefits, big. We can save a huge amount of money. We can save a huge amount of delays. We can get a better pavement, and we can help the environment as well.
Testing began in late 2025. Each section will undergo approximately 75,000 simulated aircraft passes, equivalent to the weight of a Boeing 737, to test for rutting and cracking resistance under both hot and cold operating temperatures.
Currently, there is no specification on CCPR in FAA's advisory circulars, so airports are unable to use it on AIP-funded projects. But if we test these materials here under extreme conditions, then we'll be able to put together a specification that will go into FAA's advisory circulars, and then airports can easily use this technology without going through modification to standards.
Cold central plant recycling has the potential to save money, reduce waste, and lower energy use. It's a promising, rapid, sustainable approach that's being explored for modern airport paving projects.